extending approximately 83 kilometers of stretch along the coast. So there are two modules which I have been working on, and you might be familiar with the model called Envision, where John was explaining a lot of things about Envision for the fire hazards along the bend area and modeling that fire hazards. So in this Envision module, we are mainly focusing on coastal area where erosions and flooding are simulated. It contains two modules mainly, erosion module and flooding module.
Oh yeah.
And I was like, it contains three modules.
And turned around and left. And I was like, okay.
Yeah, thanks.
Yeah. The flooding module is linked to another numerical model called the swings, which will be generating the flooding extents all along the coastal region. All these techniques are working on policies and climate change scenarios, which is incorporated with the coastal communities' knowledge we acquire through the interactions with the stakeholders. The second figure on the middle, which illustrates the modeling we are using, where a boundary point location is transformed the wave dynamics along the ocean area, and it is transformed to a 20 meters of depth at 1 kilometers of resolution, and it is again transformed to the nearshore locations at 10 meters of interval. And the last figure shows the beach type features, where we have to be aware about the coastal, backshore, and nearshore features along the coastal areas. So we try to define 14 beach type features along the coastline, and it includes the structures, the natural interruptions like rivers or bays, and the backshore and nearshore features. These are some of the preliminary outcomes we generated from the erosion model with 3 climate change scenarios, where there are multiple matrices we can generate. Some of the matrices are illustrated here, where we can assess the beach accessibility, the coastal retreat happening all over the coastal area, the events or the climate change impacted erosion happening from time to time. We are mainly focusing on long-term basis. So we will be calculating the erosions and flooding from 2020 to 2100. And this is a flooding outcome we generated along the coastal area, and this is a focus area along the Tillamook County. And the left-hand figure shows the area flooded along the entire coast of Tillamook. Though that figure, the figure in the inside this inset is showing the climate scenario we are focusing on. This is the highest extreme climate scenario we will be focusing on. You can see the animation where the flooding extents are varying when it is simulated from 2020 to 2100. And for the future work, right now we are focusing on the chronic hazard piece, but we try to incorporate multiple hazard which is happening along the Cascadia region. So we will be looking into chronic as well as acute hazard, that is seismic and tsunami inundation, which is along the Tillamook and later on to the Cascadia regions too. And that's our future work. Thank you everyone for listening carefully.
Okay, I just wanted to make sure the our members in the Zoom can hear us properly. We had a lot of issues last night, so are we good? Yeah. Okay. I don't get any responses, so I assume you guys are good.
So, just in time for my presentation, everybody is on.
I don't know if there is.
Is your
I don't hear
camera? So they can only hear us.
And there's a camera.
Oh.
There's a camera. You can wait. This one to make sure. This one to make sure.
I don't see them.
Okay.
Yes, that's it. So I don't know if they can see that.
Maybe you can ask them.
Weird, all right. And maybe it's, this page.
She's a student. Okay, this is us.
Ah,
So
okay.
we have seen.
All right, so you can see me right here. Okay, good. Now I got it. I'll just step in and out. Hi, so, yes. So I'm Derek Godwin. I'm an OSU faculty in the in the BEE department. I have an extension appointment, so I don't have a teaching appointment or a research appointment. So most of my work is out in the communities, some things on campus, but mostly there. And at the beginning of organizing the seminars, we had talked about joining up with crop and soil sciences and talking about projects that we are doing together or could possibly do together. And so I invited Christy to come along, and so she'll take over the second half. So the title that sort of meant to kind of encompass us is recent Extension Watershed Management Efforts related to large scale agriculture in the Willamette River Basin. So first, I think it's important to know a little bit about the Willamette Valley, especially if you're not from around here. So the Willamette Valley, let's go. There we go. Kind of be seen. So the Willamette Valley has roughly 70% of the population, so it's the main population corridor. As Christy was talking to Shalini ahead of time, so the Willamette Valley has a Mediterranean climate, which is cool, wet winters and warm, dry summers, which makes it like excellent growing conditions, especially with the soils and other features that we have in water supply. So the farms in the valley, most of them at the large scale, well, at small scale too, are family farms as opposed to more corporate owned. They produce the highest regional sales on only 4% of the farmland. So they're producing a lot of products that are specialty crops that are of high value. And they're number one and kind of top 5 and 10 in the US in a number of different products. A couple being grass seed and hazelnuts. And grass seed and hazelnuts are continuing, at least hazelnuts, continuing to expand the amount of acreage that they're using. So those two crops cover a lot of acreage. So with the Mediterranean climate, it essentially every summer, it just about doesn't rain. And there's essentially no surface water rights, so irrigation rights available for folks. And the groundwater is pretty limited. If there is groundwater available, it may be too salty or too difficult to get out. And also some reports have shown that agriculture uses about 80% of the available water supply. And of course, they're using it in the summers whenever we don't have as much available. And then the other part is, well, why not build reservoirs? So we do have a number of reservoirs around the valley. And so you have the potential of building reservoirs that capture wintertime runoff and store that water for then use irrigation in the summer. But for one, it tends to be cost prohibitive for so many of these family farms. And then the other thing is that the number of areas that you can do this is also really limited. So some of the crops that we have here in the Willamette Valley were traditionally dry farmed, not irrigated. Hazelnuts and grass seed being two of those. But at the same time, if you have irrigation, that's going to increase the yield, increase the quality, and then also sort of limit your risks. So if you don't have water available and you go through a dry period, then you could be losing either tons and tons of output or even losing your crop altogether. The other thing about the Willamette Valley is we grow a lot of specialty crops, meaning that there's pretty limited amount of research and on growing the crop, and especially on irrigation. And I'll talk to you a little bit about that, a few examples. Irrigation practices, we generally think of Central and Eastern Oregon as water limited, and the folks that do have irrigation have spent a lot of money and invested in their irrigation activities and equipment and so forth. In the valley, it's really wide ranging. Everything from really fairly cheap type of irrigation practices all the way up to the full linears and pivots and things. So really, really wide application. And they vary widely because of the historic weather conditions, water availability, the various types of crops, and of course, conditions. And then the other piece is that many of the streams and rivers are on the 303D list as being water quality limited. And particularly in terms of temperature, dissolved oxygen, nitrogen, and bacteria. And there's also some areas of groundwater that have poor water quality due to nitrogen. So that's the background. So what do we do about it? There was some funding available a few years ago, and we're still using some of that to start up a long-term study. There's a group of producers that had heard and familiar with studies that are 20+ years looking at hydrology and changes. In particular, there's one in Central Oregon of juniper cover and juniper encroachment and what happens if, how does that affect a water supply and so forth. And so they wanted to do something like that here in the valley. And they wanted it to focus on more of the typical surface water quality problems like stream temperature and water supply and nitrogen. And they wanted this to focus on the large scale commercial operations as opposed to the smaller farms and their operations. And so that's what brought me into this as an extension faculty, and also been working with Dr. Carlos Ochoa in animal and range sciences. And then we started this project, in the 2016 to 17 over here in Oak Creek on the College of Ag property with OSU. Started out on the pastures at the dairy center as well as the sheep center. And then we've been doing that for a few years and now expanding it up to another watershed called Salt Creek outside of the Yamhill, or part of the Yamhill River Basin. So what are the things that we're doing? Well, we have several different components, but I just have time to talk with you about one in particular, and that is field water balances. So what we decided is the first thing is that if you're going to be looking at water quality, you need to understand the hydrology of the system first, right? Or at least from a hydrologist, that's what we think of. So the producers actually wanted to understand hydrology as it relates to pollution dynamics. And then also there is this lack of understanding. The producers say, well, all we ever hear is ag uses 80% of the water that's available. So what does it mean by use? Is all the water going into the plants or the atmosphere? Or what about some of the water that may be irrigated and back into the groundwater? What does that actually, where is the water going? So we have many different stations set up, a variety of monitoring stations. And in particular, we put a couple of weather stations. So this is the weather station with Campbell Scientific data loggers and things. And that includes a precipitation gauge and, basically taking the typical weather parameters. So we have a few weather stations, and then we also put in soil moisture monitoring stations. And what we've done is we put in the soil moisture at 20, 50, and 80 centimeters in depth through the profile, with the idea that 20 and 50 is right in the crop root zone, depending on the types of crops that are grown. And then 80 sort of represents that going past 80 would be the movement down into deep percolation or towards that shallow groundwater table. And then we've also paired wells, shallow monitoring wells. And this is, of course, taking just the it's the height above the sensor, but essentially identifying where the water table is. And so the idea here is, just like many of you have learned in your courses, they're looking at the water balance. So there's one method, the soil water balance method, that is essentially the deep percolation equals irrigation plus precipitation minus runoff minus changes in soil moisture and minus actual ET. And so we're going through and measuring that in particular during the irrigation season, but also in a year round. Okay, so we'll leave that at that. So that's one of the components here. Another part of this is with the water levels, and that is using the water table fluctuation method. And that one is looking at aquifer recharge is essentially the change in water level times the specific yield of the unconfined aquifer. And so these graphs, just a little bit of sample data here. I know it's fairly hard to see, but I just want to show you. So this is one field that we have 4 different wells in, and each line is showing the water levels as we go through the irrigation season. So this is 2020 and 2021. This irrigation season, due to a kind of a variety of different things, we didn't get started until August. And so these were longer periods of irrigation and more higher quantity. Whereas in the next one, the next year, we did more of a traditional, irrigate for a day, switch to another spot, irrigate for a day. So these are the reactions to the groundwater table through the irrigation. And the other component is, so with irrigation and these impacts on the shallow groundwater, how does that also affect riparian zone stream flows and that sort of connection? So what we're showing here is a graph of the elevations have been normalized here. But what we're showing is this is an irrigated field, and then this is the riparian zone. So this, we have a station that's really close to the creek, and it's showing this connection between the irrigated field and the irrigation events and the riparian groundwater level. And then this other one is an adjacent field that's not irrigated. So 2 different test fields right next to the stream and the riparian zone. So just an example of kind of highlighting some of the dynamics here. The other thing that we work with producers on is we show them a variety of tools and equipment and what things can be used. These are just a few examples. In this one, over here at the dairy, they use just a K-line. Think about a fairly simple irrigation system here. And we have collection bulk rainfall tubes and you can't see the data of the precipitation gauge, but we have one here and soil moisture and so forth. Anyway, point being is that measuring the different amounts of water that's being irrigated through each of the irrigation circles. Flow meters, you may not realize that you actually are not required to have a flow meter here for your irrigation. So a lot of folks don't. So they have an idea of how much water they're using, but cannot actually be measuring it. This is one of the soil moisture probes that are Campbell Scientific kind that you may have seen. And this is an example of flumes. So there's a variety of flumes that you can make and use those for measuring stream or ditch flow if that's an important part of research or water management. So the other piece here is that in addition to research, what is this data? How can this data be used for their management and for the producers' irrigation management and nutrient management? So you take something that you learn from irrigation classes, looking at the field capacity of the soils and the wilting point and having this area in here that's the amount of water that's available for plants. And of course, it varies by soil texture class. So very common graph, and most of these growers have learned this as well. So but the part is that they haven't seen the actual data, and data is obviously much messier, right? It's more messy than what you would learn about. So in this data, this is the soil moisture of our probes, our soil moisture probes. The top one being 20, the middle one being 50, and the bottom one being 80 centimeters deep. And I was just doing this is January up to July for a grass seed field. And so what we talk about is how do you take this kind of data and figure out what is field capacity, what are wilting points, what are the various sort of areas that you would be managing your irrigation within. And then also, at what different stage, because plants as they grow, they go through different stages and require different amounts of water. And with grass seed, for example, and this is from last year, it was pretty wet in the spring. And so most of the folks didn't have to irrigate at all because they want the crop to actually dry down towards the end before it gets closer to the harvest. So using that for their decisions, soil temperature, which I don't have up there, but is another parameter that we provide to them. And then here's a couple of things that I printed out and are provided to them last year. And this is adding in ET rates, so evapotranspiration rates. So some folks manage their irrigation based on their ET rates. One of the problems or challenges that we have is in specialty crops, we don't have ET coefficients. So you take the measurements from the weather stations, and that is your reference, but you don't have a good factor to multiply that out to kind of understand how your crop is doing. So, but anyway, this graph is, the blue is temperature in Fahrenheit on this scale. And then the green is precipitation. So as I mentioned, this is May through July. We had quite a bit of precipitation this last spring. And then the bottom line is the daily ET, just in a reference. And then the other way of looking at it, same air temperature, but as a cumulative graph of ET, because some growers may be looking at, okay, well, over this week, what is the roughly amount of water that I need to be putting on? And so they would, instead of looking at the daily amounts, it may be easier to do cumulative. So those are a couple of examples of just taking technology and data and trying to incorporate that in working with producers. So hand it off to Christy. Bring it on. A little bit they can see you if you stand in front of the light and it blinds you. That's like the perfect spot.
Okay, so I'm Kristen Tanner. I am a field crops extension agent, and my position is county-based, which means I'm in a little office out in the county. I cover Lynn, Benton, and Lane counties. So if you ever take Highway 34 over to go to I-5, you're going to go right past my office. I cover predominantly field crops. So in this area, it's going to be grass seed, legume seed, some cereals, so wheat, meadow foam, which is the stuff that's totally white in about May in fields, and mint and a couple other specialty seed crops. And in my area, that's about a little over 200,000 acres of farmland, and I work with growers that manage that farmland. I started in this position about 2 years ago, and one of the big problems that growers mentioned when I got started was voles. This is a gray-tailed vole. It's endemic to Oregon and the Willamette Valley, and they are a huge pest of grass seed systems. Historically, we'd have high population numbers for 1 year, and then the population would crash, and they wouldn't be a problem for the next 4 to 8 years. But they were bad the year I was hired, and they have been destroying crops since then. So growers asked, for help dealing with this problem. And this is an example of what damage looks like in the grass seed fields. This is tall fescue, a couple weeks before it's ready to harvest. You can see you've got a lot of seed heads coming out around the edge. But this patch here in the center, there's hardly any seed heads there. And the general estimate is 30 to 50% yield losses, but it varies. Some of the farmers I've been working with have said, they got 400 pounds of seed off the field, And the average is gonna be about 1,700 pounds, so that's well over 75% yield losses in some fields, which is pretty substantial. And tall fescue's grown on about 150,000 acres in the Willamette Valley, so, and many other crops are also damaged. Here's a little bit more example of what happens in the fields. So this picture on the left is an example of good, healthy stand, lots of seed heads. It's pretty dense. Over on the other side are pictures of the same field, but you can see there's hardly any seed heads there. It's pretty much bare. And this down at the bottom is what the bulls do. They basically go through and they start logging. They cut those tillers down and they chop them into little short pieces. And this is what happens in other times of the year, not, when it's not right before harvest. They basically graze the grass. And, a little bit of grazing grass is totally fine with, but if you chop it down like this right here, repeatedly, that's going to wear those plants out. Basically, grass plants keep all of their extra sugars and all their stuff that helps them grow back in the lower part of their stem, the bottom 2 inches or so. And if you keep taking that off, those plants are going to be pretty weakened. We've got really limited control options for bulls. So the one option is tillage. So if you go out and till the field, they're little guys, not great for them. They either die or they leave and go to the next field over. But many of these grass crops, especially tall fescue, the growers normally want to have those in the field for 5 to 7 years without tilling that field and having to replant. And replanting is expensive. So tillage is not the best solution. We also have one pesticide product that it's called zinc phosphide. There's actually a couple different products, but it's all the same ingredient. But there's a lot of restrictions on how that can be used. During the winter months, so between mid-September, so fall, winter, and most of spring, all the way through end of April, that can only be applied by putting it underground. So you put it in the entrances of burrows. And you have to have people go out and walk these fields and apply that bait. And that takes a lot of labor. They can broadcast apply this stuff in during the summer, but overall, the effectiveness of this bait seems to be going down. There's a lot of evidence to suggest that the bulls just are less likely to eat it. We also have biological control. So red-tailed hawks are, one of the predators that's out there. I cut a picture of the coyote. The bald eagles probably don't do a whole lot for bull control, but I have a picture, so put it out there. But these predators don't reproduce as fast as bulls. Female bulls can get pregnant at 3 weeks of age. And so you've got about a 6 to 8 week generation time. And they have, 4 babies per litter. So these populations can just explode really quickly. And the predators can't keep up. So this is another example of damage in the field. As you can see, these fields are big and there's a lot of holes out there, but you can mostly just see the damage that's right around you. And if you look out across the field, the damage is less obvious. So if you imagine going out and trying to put bait in all the holes in this field, that's a big job. And also just being able to figure out how much damage is there without walking every step in that field, that's a lot of work. So my first question was, all right, what if we put a drone up in the air and try to get pictures of this damage so we can get a better measure of how much damage is out there? Of course, a lot of growers are like, well, we want to kill the bulls. We don't really need to, go through all these steps. But I'm like, well, actually, this is probably one of the best steps to take toward actually reducing bull populations. if we're gonna use any other control methods, we need to figure out if they work. And kind of our other options for figuring out if they work would be putting out traps and checking them. And this is like, the typical procedure would be a grid of 100 traps that you check once a day for a week, which is a lot of work. This can also be used as a scouting tool. The idea is, say you've got a young field that has only a little bit of mold damage, but you don't really know where it is. You could put a drone up in the air, theoretically, and figure out where the damage is, and then send guys out with bait to treat those spots before the whole field is infested. So I'm going to talk today about flights, 4 different flights on 2 different fields. So these are established tall fescue seed production fields, and I basically chose 2 that are going to look different. One is an old stand, one is a young stand, one is turf type, one is forage type, so for animal feed. And one had really clear rows, the other had plants kind of everywhere. The flights were done in late March and April. So this is the time when the plants are really growing. And so you can kind of pick out, this is basically when growers said they thought the damage would be most visible. I've got a drone with 2 cameras. One is a regular RGB digital camera. The other is multispectral. So in addition to red, green, and blue bands, it's got a near infrared band and a red edge, which is between red and near infrared. So it's light that we can't see with our eyes, but it's really informative when trying to figure out, when measuring the health of plants. So I also looked at the damage on the ground. So I went out with a GPS, an RTK GPS, which is really accurate, and I marked locations, 40 different locations for each flight, and said either there's damage here or there's not damage here. And I also used marked locations of ground control points to help link the georeference imagery from the drone with the location of the ground. So this is an example of the data. Each of these 3 panels is showing the same location in the field. We've got a natural color, so this is the higher resolution RGB imagery. The middle panel is NDVI. It's a vegetation index that compares wavelengths of light that plants absorb with wavelengths of light that plants don't absorb. And so the green area is basically represents healthy plants. The red area represents soil. And then on the far side is a cool thing that you can get out of drone imagery. It's a digital surface model. So the 3-dimensional model of the surface of the crop canopy. And it's represented here as light areas are tall plants, dark areas are short plants. So the dots, the red dot and the blue dot, are ground truth points. So I went out with the GPS, I said, for the blue dot, there's damage, there's not damage here. For the red dot, I said there is damage here. And you can see there's pretty clear differences. The damage points, the grass is smaller plants. You can see the soil between the plants. You've got a lot more variability in the NDVI index, and the plants are shorter compared to healthy plants where you've got no soil visible, nice consistent RGB, green NDVI, taller plants. So to actually analyze this, I, in ArcGIS, took measurement, basically data from a circle surrounding these points. I took basically a 15-centimeter radius circle, so that's about a 1-foot diameter. And I extracted basically average values, and also so average values for the canopy height. And then I took standard deviation also for the NDVI, which tended to be a little bit more interesting. And I took that data and I plotted it on a graph. So on the y-axis, right, is crop height. And on the x-axis is the NDVI, or basically how variable that NDVI index was surrounding each of these points. Blue points are ones that I said there was no damage, so I call them healthy. And red points are ones where I said there was damage. And as you can see, there's some pretty big differences between the two. They're separated. Overall, the damaged plants were shorter and they had a lot more variability in the NDVI index. This was statistically significant, and I saw the same result more or less in all 4 flights. So it was a consistent pattern of separating the characteristics of damaged and undamaged plants, which I thought was pretty exciting. All right, my next step was to see if I could get the computer to classify this for me. So I used an image classification, and this was an object-based and supervised image classification, which means I gave it some training data. I said, all right, this is an area with healthy plants. There's some areas with soil. There's some areas with damaged plants. I used a lot more samples than this and asked the computer to classify the image into those 3 categories. And this is what it came up with, which you can kind of see it did a decent job of separating damaged plants, healthy plants, and soil. And so I did a similar approach to evaluating how well this worked. And I took that 1 foot diameter circle around each point. And I said, all right, around each point, what percentage of the area in that circle was classified by the computer as healthy, damaged, or undamaged? And I made graphs like this. So each bar is going to be one of those ground truth points. So when I looked at all of the points that I had measured, each panel is a separate flight. So we've got one field on this side, the other field on that side, and then earlier flight, later flight. And points that I said in my ground truthing were damaged are on this side, healthy points are on the other side. Overall, I was pretty happy with how well the computer did. Overall, most of the ones that I said were healthy, the computer said were healthy, and mostly damaged points, the computer said was either damaged or soil. It did a less good of a job for the older field, and it had some inconsistencies between the 2 flights. For the March flight, it did a better job of classifying the damage, but it messed up some of the healthy. And then we got the opposite in April. But overall, even, for example, the classification of the healthy plants for the old field flight in March was 84% correct. And if I look at one of these individual points that, you'd say I basically got it wrong here. But I took pictures of each of those points. And when I went back and looked at this, I'm like, well, computer didn't actually get it that wrong. This is an example of the spot. I tried to vary, how big of a damage patch was I classifying as damage to kind of get a sense of how well this was working. There's definitely damage in there. You can see there's droppings, there's leaves that are chewed, but there's a lot of fairly vigorous plants surrounding it. Overall, the accuracy was pretty decent, about 90% accurate. And I'm saying that, areas that were damaged, there's a lot of soil surrounding those damaged areas, as you saw in the earlier pictures. So I'm saying if the computer says that's soil, well, that's mostly correct. And so we had 9.4 and 7.5% of incorrect classification. So overall, I was pretty happy with this result. To conclude, I saw pretty clear differences between plants that I had said were damaged and plants that I said were healthy. Damaged plants were shorter, and we saw a lot more variability in the imagery in the NDVI indices. And overall, image classification was able to do a decent job of differentiating between areas that were damaged and not damaged. Thanks for having me. It's really great to get a chance to speak with you guys. And this is my contact information if you're interested. And I really appreciate my colleagues that have helped me out and funding sources.
Very cool presentations, maybe showing, how it's using artificial intelligence to tackle some of the problems. Yeah, thank you. Do we have questions for our speakers?
Yeah, I have a question. So at the beginning, you said that typically the population like explodes and then crashes for a few years and it's cyclical in that nature.
Yeah.
But it's not like that currently. Do you know why? Any hints why?
There's some guesses. One, people have thrown out climate change. They've thrown out things like, grass seed producers used to be able to burn the fields. And that probably had a pretty strong effect on vole control. They're not allowed to do that for the vast majority of acreage for air quality reasons anymore. And so, there's a lot of the growers be like, well, if we could burn, we'd use a lot less pesticides. And I'm not quite sure where that balance would end up, but so that's one possibility, climate change. Another thing is maybe they've kind of learned and evolved an aversion to the bait. So they used to be, farmers would have said, I used to go out and apply bait, and you come back across the field and there would be dead bulls already. And that's not, most growers don't report that anymore.
Yeah, I have a question. So did you think about wondering, how we can maybe enhance the efficiency between the damaged plants versus soil? So do you think that if you put like internal imaging cameras that would pick up those signals better between plants versus bare soil?
That might, one issue with thermal imagery, so you end up with a lot lower resolution. So that's kind of a balancing act. It'd be fun to get my hands on a thermal camera.
Thanks. Yeah, it's kind of in line with what Shalini was saying, and what you already touched on a little bit, but I was wondering if you used satellite imagery, so even the coarser spatial resolution, if you will be able to see, do you expect to be able to see something? Because I would assume that that's easier for farmers or growers to use and having to fly drone and, and less data.
It depends on the resolution. So, and I'm not quite as up to speed as I should be on like what is sort of the better resolution satellite imagery that's readily available. Some of it's 30 meter, which wouldn't do you any good. We can go back.
So what kind of spatial resolution do you think you'll need?
So the rows are 15 to 20 inches apart. And a lot of the patches of damage, they can be small. Like I showed in that one picture. The larger patches of damage would be as wide as this table is pretty common to see. So you would need at least meter resolution, and that might get you something, but probably lower resolution than that, especially if you're trying to say you've got a new field and you want to target new vole infestations. You want to catch them when they're smaller to be effective.
So very nice work. I have got one point, to improve your prediction. Is it the alternative, algorithm can do something? Your classification algorithm?
Yeah, so trying different classification algorithms, is that what you're?
Yeah,
Yeah.
and also increasing the ground truthing point, training area, training categories, training variations. Will it make sense?
Yeah, so there's definitely more experimenting I could do with different algorithms, with different, how do I break up the categories? And I haven't had time to do that yet. Unfortunately, my position doesn't really have a explicitly research component, so my time is a little bit limited. I originally tried to do just damage and healthy and tried to, mark off bigger patches of the field. And that I ended up just getting the, soil, what the algorithm gave back to me was basically soil and plant. So I think there's definitely room to improve there, but it's gonna take some work.
I'm gonna have two different things. One of them is like your experience with the farmers, like obviously if the wolves are that's money for them. So do you ever experience like pushbacks or like things that could affect your research otherwise?
Yeah, so actually I got three farmers, and one of them had 2 fields with a 5-acre plot where they didn't apply bait last fall or 2 falls ago, which I really appreciated. And I definitely I could tell that, one of the farmers, he'd come over and be like, it looks pretty bad out there. He ended up, it sounded like so they can get yield maps from the combines, and he said, well, it wasn't actually the spot where I didn't apply bait that was the worst in the field, so. So the growers, they would prefer not to, have those control plots, but they understand research and they understand that this is a big problem, and so they're pretty supportive of people working on those problems, and if they have to give up a little bit of their field to help move that cost forward, they're usually pretty willing.
And then my second part was opening it into like a citizen scientist. I know there's a lot of like choral projects on research and stuff where they have like pictures and the person will like help clarify, like they'd be like, this is soil. And this is, have you thought about opening it up into letting people do that?
To like have people classify these images. I
Just to give the
haven't,
computer more info.
I haven't, and I think my concern is that it's hard there's a lot of variability in what this damage looks like I go from one field to the other and be like, well, I originally tried with a grades like 1 to 4 of how bad the damage was, and that's just like, well, now I don't really know where I am because this field looks different, and so I ended up I took pictures and ended up going the simple, this is the patch of damage, this is a patch of, these plants look about as healthy as they can get. To try to simplify that. And I still haven't I'm not sure that I've found the best approach. But that would be kind of my concern with the citizen science, is that it's hard to be consistent in those sort of rating schemes.
On the question that line, so you had data for like, let's say April and May, so 2 separate events. So when you created your supervised classification, did you create it each time per event, or did you create it on one event and then also use it at the same classification for the second?
Separately for each flight.
Separately for each. And then I'm assuming like one of your last slides, you had, is it like an error matrix?
Yeah.
Right. I noticed that on the soil, I think, was excluded on one of the axes. Is that a deliberate choice?
So, yeah.
Okay. Just get, you're already in this.
It's like a chart, I think. the last
Yeah.
year.
So,
Or how do you?
yeah, so. Yeah, so you're talking about the soil for healthy, correct?
No, for like soil to soil, if you have healthy to healthy, damage to damage. and things like that. Yeah.
Yeah, so when I was out there with my GPS, I didn't mark soil specifically, I marked damage and non-damage.
Got it.
And, I think that it's pretty obvious in the pictures where soil is, and. Yeah, I mean, maybe that would have been helpful, but I think this is the data I collected, so.
Just very, thank you.
Tarek, I have a question to you. So, again, going back to the extension component here. So you have mentioned about, some of the goals for the project was to really verify that whether 80% of the water being used for agriculture and we are having the return flow going back to replenishing the groundwater sources, right? And so based on your observation, whereas, maybe not conclusionary yet, but how did that information be taken back to the farmers and what was kind of the reaction to that? So I'm curious, maybe often. point figures.
Yeah, well, and the 80% was more of just, that's just kind of like what we weren't trying to verify that or not, it was more of just trying to capture. Where is the water going? And I would say that the growers were kind of like, I told you. But I think there's still a lot of unknown there because the connection to the shallow groundwater is much stronger than I think people had imagined, especially like in clay soils. Because in clay soils, the assumption is, well, water is not going to move very fast. It's, because they're thinking of this full blocks, this soil matrix. But in reality, there's cracks, there's macropores, so there's a lot quicker connection, a lot more direct connection there. And then also we'd like to do some more work in the riparian zone. I think that was, I think people were surprised to see that. Because that graphic was actually over here in Oak Creek, again, where there's a lot of clay soils. And if you look at the distance there, say 100 yards or something like that, you're still seeing a pretty quick response. I mean, we don't think it's the same water that's coming in, it ends up over there, but, kind of pushing it through kind of thing. And so and there's just a lot of interesting connections there, I think, to follow up on. Yes.
Yeah, so you analyze 3 of the landscapes or the irrigation practices, no irrigation and riparian zone.
Oh, yes, okay.
So for riparian zone, how much was the groundwater contribution to the ET company?
How much was the groundwater contribution to that?
Not ET.
Oh, to the ET. Well. We're not really sure because, honestly, we're only taking the ET off of the weather station, and that's a calculation of that. I think, okay, so you mean like, are we seeing that within our moisture meters of what's coming up out as ET?
Yeah, for ET there will be 2 contributors like root water upgrade from the aerogen and from the groundwater. In riparian zone, there will be a lot of contribution coming from the riparian zone and the shallow groundwater. So have you got the segregation between them?
Yeah, I'll have to talk to Carlos on that and see how he interprets that. I'm not sure. Yeah, so that's a really interesting question. Have to go back and take a look. So I do know that. So one of the things that happen in these fields because they have high clay content is that whenever we irrigate, if they're irrigating, a lot or too heavy, it'll pond really quickly. And so, so that of course is going to contribute to the evaporation. And I have to go back to see if they kind of have some better estimates on what they think is a contribution here, but we noticed that especially in the first year, because we couldn't get, they had some equipment problems, so we couldn't get going on the irrigation. Usually you want to probably start in like June or July. This didn't happen until August, and so there was it was pretty heavy irrigation trying to get that soil profile moisture up. And so there was a fair amount of ponding, just kind of little bits that are sitting there. Yeah, I'll check into that. Yeah, thanks for that. Interesting.
Great, thank you so much for all the speakers.
Folks. I didn't see that, I couldn't do it. But I wonder how much, let me see. Yeah, I mean, I guess they can get. I just wonder what kind of experience they have. Bye.